So I posted this comment on this video. I can't remember quite what it was. I think it was something to do with. No, I do remember what it was. It was something to do with the latest observations of the effect of light caused by lunar dust. And I thought I was really clever in the comments by bringing up what I knew about, or what I thought I knew about Arthur Eddington's observations of this solar eclipse in 1919 that acted as the first bit of evidence really for general relativity, this theory of Albert Einstein's. And someone corrected me in the comments saying like, oh, they weren't measuring like distortion caused by the moon with the light from the sun. They weren't measuring that. They were measuring distortion caused in the light from other stars behind the sun by the moon in a by the sun in a lunar eclipse. It's like, I don't see how that makes any sense at all. I really don't. And now, obviously, if we're doing experiments with like lunar dust, yeah, right. And in these 1919 observations, you have the distortion of light from the moon's surface. And remember, like in a solar eclipse, you've got the moon there, and then the huge, great whacking sun behind it, and then you've got these like tidbits of light, like these eensy weensy little bits of tiny light from distant stars entering the sun's gravitational field, and we somehow detect them in a photograph by Arthur Eddington in like off some or some African country in the southern hemisphere, in the Pacific Ocean, Atlantic or Indian Ocean, whatever, right? But like, no, how that's not evidence of general relativity. No, it isn't. Of course, it isn't. If anything, that's a distortion due to lunar dust in an eclipse, or isn't it? Like, I don't think they were like doing very advanced. I mean, kind of teasing apart of this. Like, yeah, here's like the picture that they got. They got HR1403. Why does it make sense that light is from any of those stars? You know, the constellation Taurus there with 4 stars, okay, but there's not as much light in that part of the photo. Why is this evidence for general relativity? And like, and moreover, more to the point, like, actually, would the moon's gravitational field not have an effect? It would have no effect on the light. I mean, I'm just thinking because okay, so you've got an eclipse, right? I mean, the sun, right, shines light on the moon. Almost all of it bounces straight back from the other side of the moon back into space. Almost all gets reflected. And yeah, I can imagine like the albeit very weak gravitational field of the moon. Yeah, it does cause some diffraction with the light. And the dust, if we think that lunar dust really does cause this, yeah, it would. And I don't know, like, I think there's kind of like a thing going on in people's minds, like they really, 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 really want general relativity to be correct all the time. You know, it's like there's this dogmatic relativism, and like, you know, it has to be like, you know, going in some like curved trajectory into a stupid trampoline space-time curvature puddle or something, and then out the other side, and it can't be like deflected and, you know, channeled through a cloud of particles, like a quantum gravity sense, and it could be reflected off a cloud of particles either. Yet it would be, because I mean, we track like the way that gravity works from, or like the way that light interacts with, say, things like atoms from the atomic scale. You see under the microscope, you see a cloud of an electron, or some electrons, some small number of electrons surrounding the nucleus, light's all bouncing off it. We see the Earth, like light's bouncing off that. See, well, the sun mostly emits light, but yeah, light also bounces off it. It'll at least bounce off the atoms in it. If you get close enough to it, it'll hit, yeah, most certainly will hit electrons. The light will, and it will bounce back. That's certain. They're like, what my idea for quantum gravity relies upon is like, yeah, like there's a point at which we definitely know there are electrons there, very close to the surface. It's like retreating from the surface, going say, a few thousand miles back in space. Like, there's like the electrons are existing there from the planet, say, for about a Planck time each time. So we can't detect them directly. So I have to sort of infer their existence. So like trust that they're there. We can't really observe them quite so directly as we can under an electron microscope on the surface of the planet. See what I mean? I don't think it's unreasonable at all, given how many electrons comprise objects like a moon or a planet, to state that, yeah, they're almost always near the surface of the planet, or almost always in this regular region around the atomic nucleus. But sometimes, in a very, very small number of occasions, they're outside that by quite a substantial margin. Or there's a probability that they can exist out there because they change position so often and there's so many of them. The probability of this very unlikely event occurring eventually approaches unity, approaches certainty, and it approaches certainty more than once, or many, 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 countless numbers of times. Yeah, even in a second, I calculated like some 5.53 times 10 to the 53 times, or 53, so let's say virtual electrons comprising gravitational field. And reflecting light, exchanging particles, doing gravity stuff. And yeah, it's not this silly trampoline of Einstein's. That Arthur Eddington experiment is such unbelievable bunk. I think that's probably one of the reasons why Einstein didn't get the Nobel Prize for general relativity, isn't it? Because it wasn't considered like a strong enough base of evidence. They were like, yeah, well, lunar dust could queer all sorts of things. But general relativity is fucking stuck around, even though it's a crap theory. And it's like, it's just curved space-time. Like, what the fuck is space-time? Why does it curve? Oh, it curves in the presence of matter. Why does it? Like, you just say, like, space is matter. Space is at least energy. Space is saturated with energy and fermions, by the way, and atoms and plasma and stars, planets, galaxies, and whatnot. There's no actual space in the universe, I don't think. No, not real empty space, but just particles, a superparticle. That's what we live in. I think that's pretty obvious anyway, isn't it? So yeah, I mean, it made me think of something like that. I think I'd experienced being wrong about something. That's good. So I learned something. That's good. And I had an insight. These people back in 1990, they were fucking clueless. Not any idea what they're talking about. Like they think they're going to measure, like in an eclipse, with this humongous background of this enormous, like huge amounts of radiation pouring out of our star. And they're somehow going to detect the distortions by the star's gravitational field of tiny pinpricks of light, many millions of light years away. It never happened. It's ridiculous. Would we even try it today? We don't have like the satellites, Planck satellite, and things like this. We can point at the moon and do it all again if we want. Like, are we actually equipped to redo that experiment, reconfirm those results today? I don't know. Like, it'd be interesting to see anyway. See, bye bye. Thank you.